Hello, everyone. Thanks for joining us for this brief tutorial and video on the ScitKitLearn library for Python. After you may have cleaned your data using some of the packages that we've learned about previously, such as pandas or NumPy, you can use ScitKitLearn for building machine learning models. It's arguably one of the most important libraries in Python for machine learning. It's widely used and it's got lots of documentation. It also has a ton of tools for predictive modeling and analysis. So obviously there are many reasons to use ScitKitLearn, but this presentation will only be able to name a few. Hence, we invite you to check out the ScitKitLearn website, which curates a great overview of applications compiled in a handy user guide. So if you have any more questions after this presentation, we invite you to go over to scitkit-learn.org and check out some of the examples and the user guide that gives you an overview of its various applications. So before diving into a hands-on demonstration of ScitKitLearn, we want to briefly introduce some of the underlying concepts in machine learning. Here we focus on the difference between supervised versus unsupervised learning. The main distinction between the two approaches is the use of labeled data sets. To put simply, supervised learning uses labeled input and output data, while unsupervised learning does not. So in supervised learning, the algorithm, quote unquote, learns from the training data set by making predictions on the data and adjusting for the correct answer. While supervised learning models tend to be more accurate than unsupervised learning models, they also require a lot more upfront human intervention to label the data appropriately. In this case, for example, we might label this scenario or this object toy and this object not a toy. So we can predict certain things. A supervised learning model can, for example, predict how long your commute will be based on the time of day, the weather conditions, and so on. But first, you have to train or tell the algorithm to know that rainy weather would extend the driving time and therefore extend the commuting time, because inherently this is not clear. So one of the obvious drawbacks here is that the supervised learning models can be time-consuming to train, and the labels for input and output variables require some level of expertise. So why can't we just let the algorithm do the work for us? Unsupervised learning models can have wildly inaccurate results unless you have some sort of human intervention to validate the output variables. So unsupervised learning methods work on their own to discover the inherent structure of unlabeled data, but they require some human intervention for validating the output. For example, an unsupervised learning model can identify that online shoppers often purchase groups of products at the same time. However, a data analyst would still be needed to validate that it actually makes sense for a recommendation engine to group certain objects together, such as statistic textbooks with an order of a box of tissues. Let's give you a quick general overview of the main applications of ScitKitLearn. And the two main things that we want to introduce today is classification. So a typical example of classification would be identifying which categories an object belongs to. So spam detection, for example, is an email that is in your inbox or sent to your inbox a spam email or not, a yes or no scenario. On the other hand, regression is used to predict an attribute. One example here could be stock price prediction or a weather forecast. So what is the value of a stock that sold for 50 euros per share today, tomorrow? And what will it sell for the next day and the next day? So here we're looking at something where one specific prediction is made for one attribute. And both of these models are examples of supervised learning. We can also do clustering and model selection, dimensionality reduction, and pre-processing. These are a bit more stats heavy, so don't worry if not all of these make sense intuitively to you. Today, like I mentioned, we'll be focusing on regression, and these ones are just kind of important and interesting for you to know going forward. So clustering is taking an automatic grouping of similar objects into sets. Customer segmentation is an example. So I'm sure you've seen something like this before, where customers who bought this item also bought another item, and they're probably like this or that. So this is an example of a clustering use or clustering application. Model selection is comparing and validating parameters in models. It's a bit deeper. Statistically speaking, I guess, we're looking at different models or the best solution where we can compare different models and improve model accuracy through different parameters and fine-tuning. Then we have dimensionality reduction, where we are reducing the number of random variables to consider, which is used to increase model efficiency. So if you think about a data set with thousands of columns of data or thousands of features, some of these may actually be duplicates or maybe redundant. So you can combine them into single columns and therefore reducing the amount of overall columns and increasing the efficiency of your model so it can process faster or be less biased. And lastly, pre-processing, dimensionality reduction is a form of pre-processing, but another application of pre-processing could be transforming input data such as scaling or normalization. And for our demonstration, we'll actually be looking at pre-processing using ScitKitLearn. So with this sort of background, let's dive into our demonstration of the ScitKitLearn library.
Okay, so now we come to our coding example, and we firstly want to conduct a simple linear regression with the help of ScitKitLearn. And as you heard in Mark's introduction, ScitKitLearn is a powerful package, and the second presentation by our colleagues will introduce you to further functions, but we want to start with the basics and a simple linear regression, which is, as most of you probably know, based on a function y equals mx plus b, where b is the intercept and m is the slope of the line. So basically, the linear regression algorithm gives us the most optimal value for the intercept and the slope by fitting lines and determining the one with the least error. And in our example, we want to predict the percentage of grades of MDS students based upon the number of hours they spend in the Hertie makerspace. And for that, we use a small toy data set. And firstly, we need to import the following packages so we can conduct our data exploration and analysis. And we also load the data set which we're using. And so first we want to have a look at our data and explore it a bit to know what we are working with. So we want to see the shape, so we can see that our data set has 25 rows and 2 columns. And we can also have a look at the first rows to see how it's built, and also put point describe to see some statistical details. And we now want to plot the data and therefore use the pandas function, the plot function, which gives us the following graph when we run it. And this graph already lets us know that the data has a clear linear relationship between hours spent in a makerspace and the percentage score of MDS students. And in our case, the hours in makerspace determine the grades. So we can split the data into attributes and labels, so into independent and dependent variables by using the pandas alloc function to select the columns. That's what we're doing here. And we also want to split the data into training and test sets. And here we use our first scikit function, ScitKitLearn's built-in train test split method, which you can see here. And we can use the test size variable to specify the proportion of test and training set. And here we want to put 80% of the data into the training set and 20% of the data into the test set. So we put 0.2. Okay. And with that said, we are ready to run our model. And this is really straightforward with ScitKitLearn. We just need to import the linear regression class, instantiate it, and use the fit function together with the training set we just created. So now we want to figure out the intercept and slope calculated by the linear regression algorithm. So we execute the following lines of code, and it gives us the intercept and coefficient. And the result shows that for every unit of change in our studied in the makerspace, the change in the grade is about 9.91%. So our model is all set now, and so we can use our test data and see how accurately our algorithm predicts the grades. The ypred is a NumPy array that contains all the predicted values for the input values in the X test series. And now we can create a data frame that compares the predicted and the actual values of our test set. This is what we are doing here. Oh, I didn't run that one. So we're doing that here. And we can see that our model did an okay job predicting the actual values. And last but not least, we can use scikit-learn to evaluate our model by calculating the mean squared error, the mean absolute error, and the root mean squared error. And if we run that, you can see the results here. And of course, this was a very simple example, and in reality, there are way more variables that would influence our grades. But the good news is that the multiple linear regression looks extremely similar. We can use the same functions to get multiple coefficients and determine which variables determines the output most. And with that said, now Anna will go through some more useful scikit functions that you'll hopefully find interesting.
Hi, everyone. Let me now guide you through two transformations that you'll for sure come across soon. The first one is standardization, so putting everything into one scale. It's particularly useful when we're comparing many variables. So in here, if we were to compare different cohorts with different characteristics, we would probably have to control for other variables than just spending time in makerspace. Makerspace. Therefore, let me here show you how we would have to do this. So obviously we have to firstly download the package and the modules. And secondly, we are using the standard scalar function. We have to firstly assign it to an object, and then we use the fit function. And as you can see, nothing has changed at this point. We have the same data, and as you can see, the mean is still 4, and the standard, the variation is still 2. It is very important to use this fit, as then we would not be able to transform it without. So using this method, as you can see, now within this I have this fit function, and then I'm using transform. You could also use fit transform, but I think it's now easier to use it in steps. So as you can see, we standardized our data, and we expect it to be correct. So now if you have a look at the mean and standard deviation, yes, we actually have the result equal or super small, equal to 0, and then standard deviation of 1. Another form of transformation is normalization. Again, we follow similar steps. However, we need to dimension data. So I created here a little array, so you can now see how this process works. Without going into much detail, there are 3 ways or 3 norms that you can apply in Python. It's norm 11, 12, or max. We will learn about it next term, but I want to just show you how simple this process is. So we select a norm. Here I picked norm 11, and in Python it's 1. And as you can see, our array was standardized. And if this was correct, using this method, after adding these variables in the same rows, we should have the value of 1. And yeah, here we go. So it was correct. But again, we can use exactly same steps as before with standardization. So we can use the fit transform option, and it gives us the same result. But again, it was quite important to show the whole steps so you understand the logics. Yep. Good luck with your transformations and see you in class.